How's it going, everyone? Here we will explain the concept of moles and molar mass. Here we're talking about moles in the context of physics and chemistry, not about the skin formation. So to put it simply, a mole is a word that refers to a specific amount of something. Like a couple is 2 and a dozen is 12, well, a mole is approximately 6.02 times 10 to the power of 23. It's a huge number. It's just over 6 followed by 23 zeros. And this number is called Avogadro's number, or Avogadro's constant, named after the scientist Amedeo Avogadro. So what is so significant about this number that it gets its own special name is the fact that 1 mole of protons, or 1 mole of neutrons, or 1 mole of a mix of protons and neutrons weighs 1 gram. And that makes moles a very convenient amount to use when doing many different calculations in particle physics or in chemistry. For example, we could ask, how much does a mole of carbon weigh? Well, carbon has 6 protons and approximately 12 is its atomic mass, right? So protons plus neutrons should equal 12, so it has 6 protons and 6 neutrons. So a mole of carbon will be 6 moles of protons plus 6 moles of neutrons, which is 12 moles of protons and neutrons combined. And if 1 mole of protons and neutrons weighs 1 gram, well then 12 moles of protons or neutrons will weigh 12 grams. In fact, how that number, Avogadro's constant, was originally defined was through carbon. It was defined as the amount of atoms in 12 grams of carbon-12. Carbon-12 being the isotope of carbon that has 6 neutrons, and hence 12 protons plus neutrons in its nucleus. Let's pick something else. Say helium. Well, helium has an atomic mass of approximately 4, so it has 4 protons or neutrons in its nucleus. So a mole of helium will be 4 moles of protons or neutrons, so its mass will be 4 grams. A mole of hydrogen. Well, hydrogen's atomic mass is 1, so a mole of hydrogen will be approximately 1 gram, a little bit more. Let's take our last example here, oxygen. Okay, so oxygen's atomic mass is 16. It has 16 in total protons plus neutrons in its nucleus. So 1 mole of oxygen will weigh 16 grams. Now, this is very easy for just individual elements because whatever the atomic mass is, that is how much this element will weigh. So for example, 1 mole of zinc will weigh approximately 65.38 grams. But we could do this not only for individual elements, but for other particles. For example, water, H2O. And we could ask, well, how much will 1 mole of H2O weigh? Well, what does H2O consist of? Well, we have a hydrogen, and another hydrogen, and an oxygen. So, how many protons or neutrons are we dealing with in total? Well, we have the atomic mass of hydrogen, which is 1.01, but we have 2 of those hydrogens, plus the atomic mass of oxygen, which is 16. So in total, we have 2.02 plus 16, which gives us 18.02. So that is, on average, the number of protons plus neutrons that we have in one particle of H2O. And 1 mole of that will weigh how much? Well, 1 mole of H2O will weigh 18.02 grams. From this, we can define the concept of molar mass. Molar mass is the mass per mole. Specifically, it's equal to the mass of a substance divided by the number of moles. Number of moles is represented by a lowercase n. And when we're talking about number of particles, we use an uppercase n. So the number of moles itself is defined by the number of particles divided by Avogadro's constant, sometimes depicted as capital N subscript A, sometimes depicted as capital N subscript 0. Capital N by itself is the number of particles. Easy way to remember it is the number of particles is bigger than the number of moles. So that's why capital N is the bigger number of particles, and number of moles, lowercase n, is the smaller number. We've already calculated molar mass for a number of different elements or particles. The molar mass of H2O we've determined to be 18.02. The molar mass of helium we've determined to be 4. The molar mass of hydrogen we've determined to be 1.01. And the molar mass of carbon we've determined to be 12 approximately. And all of these are in units of grams per mole. These are the calculations we were doing earlier. How many grams is 1 mole of hydrogen? 1.01 grams. How many grams is 1 mole of carbon? 12 grams. And so on. As another example for something we haven't done yet, well, what is the molar mass of oxygen gas? O2. Well, we know that the atomic mass of oxygen is approximately 16, and O2 has 2 oxygens, so that gives us 32. So the molar mass of oxygen gas is 32 grams per mole. In other words, 1 mole of oxygen gas, if you have 6.02 times 10 to the 23 particles of oxygen gas, that will weigh 32 grams. So one kind of example that you could solve with this kind of information is how many H2O particles are in 2 kilograms of water? Well, first we can say that 2 kilograms is 2,000 grams. And we know that the molar mass of water is, as calculated above, 18.02. Again, how did we get that? Well, 2 times the atomic mass or molar mass of hydrogen plus 1 times the atomic mass or molar mass of oxygen. And that gives us 18.02. 1 mole of H2O will weigh 18.02 grams. So, how do we get to number of particles from there? Well, we know that molar mass is the mass per number of moles. So, we can conclude that 18.02 grams per mole should equal the mass of the water, which is 2,000 grams, divided by the number of moles. Rearranging this equation by multiplying both sides by n, we have number of moles times molar mass equals the mass of the total substance, right? So from that, we can then divide both sides by capital M, and we get N equals, lowercase n, equals mass over molar mass. All three of these are the same equation, just written to isolate a different variable. So N, the number of moles, equals the total mass, 2,000 grams, divided by the molar mass, 18.02 grams per mole. And when we work that out, we get approximately 110.99 moles. Now, from that, we want to find the number of particles. So we know that 2 kilograms of water will have 110.99 moles of H2O particles, but how many actual H2O particles will there be? Well, we know that the number of moles equals the number of particles divided by Avogadro's constant, 6.02 times 10 to the power of 23. Now, this is an approximation to 2 decimal places. In scientific notation, depending on what your application is, you might go to more or less than 2 decimal places. We'll use 2 decimal places for the purposes of this video. So, rearranging this equation to solve for capital N, number of particles, we first multiply both sides by 6.02 times 10 to the power of 23. And we've now isolated for capital N. So both of these are the same equation, just rearranged to isolate for a different variable. So number of particles will equal the number of moles, 110.99, multiplied by Avogadro's constant, 6.02 times 10 to the power of 23. And when we work that out, we get approximately 6.68 times 10 to the power of 25. That's just under a 7 followed by 25 zeros. That's huge. That's how many particles of water, particles of H2O, there would be in just 2 kilograms of water. 2 kilograms is about 2 liters. So if you imagine a 2-liter bottle of pop, which is mostly water, how many particles of H2O are there? The number is about 7 followed by 25 zeros. Why 7? Because 6.68 rounds to 7. So I hope that helps understand the concept of moles and molar mass, and until next time, enjoy.